Okay, so we have loaded up our long data set. This is the data set that we were looking at last week as well. Just out of curiosity, anybody remember what our slope was from last week? I'm just kidding. Uh, so when we set this up, we are going to set this up a little bit different. The time is exactly the same as it was before. Um, and we can modify time similarly to how we did it before. Not exactly the same as how we did it before, but we're not going to worry about that just yet. Like what we do with latent growth curve modeling and everything else that we've done so far, we have to name the variables that we're going to use in our analysis. And for this one, we're going to use time and new t, or t and new t, I guess, or newt.
Does it matter that cluster equals ID, but it's not included in USAR?
Yeah, it doesn't matter. Actually, you shouldn't have it in your UseVar. There are some things that you don't want to include in UseVar. If you put ID in UseVar, it's going to try to calculate a mean and a variance for that, and then we can throw it in once if you guys want to see what happens. You'll get error messages. You don't have to include clusters in there, and in fact, it's very similar to the way that we can do stuff in define and not actually use the variables listed in UseVar for our define variables, right? So we have actually I think new t is where let's do this. Let's use time. You guys have time, right? It's one of your variables or no?
Yeah.
Okay. So we have time, we have t. Let's set time as our within subject variable. Between subject, we're going to have nothing right now. Our cluster is ID. For analysis, we will put type equals 2level, and you can put 2level random, or you can just put 2level. There was a change, I think, recently where you don't have to list random anymore.
ID in the USAR.
No, don't put ID in UseVar.
But you can use it even if you don't have it there?
Yes. All this is doing is saying like the data are clustered within this variable. If you put it in UseVar, you will have problems. It'll try and generate a variance and a mean, and it will tell you that ID is uncorrelated with all other variables in the model, and you'll get error messages. We can throw it in if you really want to see it pulling.
That's fine.
Okay. Then we move down to model. And so when we're doing the model, we have to specify both a within and between portion. Now, technically, you don't have to, I don't think you have to specify S and T here or S with T, but you might have to. This is essentially our latent growth curve model, right? We have, this should be time. We have T on time. T is our outcome, whatever that is. S specifies that we want a random slope. And that slope is going to be T on time. Now, just to go back to the different types of variance that we have here. If we have 10 people and 10 of these T on time things, and let's say that time has 10 days. How many slopes do we have total in this model?
10 people over 10 days?
Yeah. 100 slopes, right? In the level 1 portion of the model. And we're going to get a level 1 component then that says that our slope at level 1 is x, whatever x is, and that's the average. Before we do it, let's do it before I talk through it. Let's do that. Okay, so then when we correlate this down here, S with T, what are we actually correlating? What is T? We can call T whatever. I mean, T is our outcome variable, right? let's rename it just so it's not confusing. How about we do that? Define T equals what? Happy.
Would it be the other way around?
Yep, thank you. Happy equals T. And then let's come up here and change this to happy. And then let's change this to happy. And let's change this to happy. So now, when we do a latent growth curve model, you look at this, I'm actually missing one parameter here. What am I missing? No, from this right here. The errors there, I drew them. Yeah, right. We have a covariance between these things, our residuals, right? And so S with happy is really just allowing that covariance at level 2. And so if we now hit save and run, should have run. Now in M+, we have 2,000 observations. Our time goes from 1 to 4. Here are our fit statistics. What can we gather from these fit statistics? Basically nothing, right? Like they tell us almost nothing. This is one of the problems with multi-level modeling versus latent growth curve modeling is you don't get any type of model fit. You can get ICC, you can get some interesting things, you can get an R-squared or a pseudo R-squared, but you don't actually get any type of fit statistics because this is basically a regression model, right? And if you run a regression model in M+, you also will not get fit statistics for it. All right, but our model converged normally, everything looks good. And as we scroll down here, we have our residual variance at level 1 of 0.488. That is the average amount of variance within person, right? And then we have our residual variance down here, which is the average amount of variance between person, and it is statistically significant. And this is what we call our random variance, the amount that things vary across people. And then we have these things, right? Here's our intercept, minus 0.503. This slope actually should look fairly consistent, right? It's the same slope we had last week, 1.026. And then we have this correlation between our slope and our intercept, minus 0.094. And we're missing something that we used to see for latent growth curve modeling, right? I've already said this thing, but in latent growth curve modeling, we get residual variances for each time point. We don't get that here. We get this, which is our residual variance at level 1, right?
A small question, kind of, I don't know how relevant it is.
Shoot.
Like normally we say random effect is something which changes in equation.
Yeah.
So, and residual variance is actually kind of fixed. Why do we call it a random variance as well?
So it's the residual variance at level 1 is going to be fixed. It's not technically random. The random portion is the difference between all of your variance at level 1 from your mean variance at level 2, right? So if you have 100 slopes, we were doing this thing with 100 slopes, right? The residual variance is saying like, okay, so if we have 100 different slopes, here is the variance across, here's the average variance across all of those 100 slopes at level 1, right? Level 2 is saying, now we've fixed 10 slopes, right? What is the difference between the variance of those 10 slopes and the variance of the 100 slopes in level 1? And that's your random variance, right? The amount that you can't account for by the mean level of level 2 and the total level at level 1. Does that make sense? Yeah? Cool. All right. Let's do something else here. So can somebody write this down for me just real quick? Our BIC is 6079.001, sorry. And our log likelihood is minus 316.698. Is somebody writing that down? Raise your hand if you're writing that down for me. Okay, so somebody's writing those numbers down. Good. All right. Let's grab class 1 wide. That is not it. Also not it. Oh, I think I have to go back to last week's from mine because I don't think I have. Is that right? I don't want that. The class 1 wide one. I don't have them saved in the same spot that you guys do. I think this is it though. 0, 1, 2, 3. Just run this quick. Get rid of group. It does, huh?
We don't even have columns.
Yeah, no, I had to go to a different thing. Okay, your class 1 wide has T.
T1, T2, T3, T4.
And then
That's what it's supposed to be. My stuff did not. Hold on just 1 second here. Maybe it's in week 12. Nope, that's not it. Nope. Ugh. I'm sorry. I think this is where I'm supposed to be. So if you guys run class 1 wide, what is your slope? Just real quick. Wait, does it look like this? T1, T2, T3, T4?
there's just no C's or N's.
Then it's probably not. That's probably not right.
So for what? Which one?
If you just run the...
Should we be setting the syntax up the same
Oh,
way?
does it look like this?
Yeah, but we don't have group, we have ID.
All right.
So then it's set or?
If you run this model right here, let's just do this. 0, 1, 2, 3. I just want to make sure that my data matches your data. Do you get a slope of 1.051? Is that right? No, the last slope that I had was 1.026. Is that what you guys get? 1.026?
Can you ask your model? And what value is it?
The slope, S, mean of S. Is it 1.026 or 1.051?
1.026.
Shoot. Okay, then this is the wrong data set. Hold on, I'll just download the other data set. Rather than do this over and over, let's just grab that and grab that and Dropbox. T3. Week 11. Oh, you. Okay, there's my input file. It says it was in there. I couldn't see it. And there's my data file. Also says it's in there and I couldn't see it. I don't know. All right, so now we should all be the same. That's what your guys' look like? Okay. Okay, IS T1, T2, T3, T4 at 0, at 1, at 2, at 3. This is what everybody else has? So yours looks like? Let's run that one. What's that?
We're using all the variables.
Oh, no. See, it included ID in there when I did that. Yeah. Thank you for that, though. Use var is T1, T2, T3, T4. All right. Now let's run this. Okay, our slope 1.026, our intercept is 0.523. I want you guys to keep this up. I'm going to open up the multi-level model that we just ran, and I'm going to run the exact same thing, and let's compare our parameters here. So let's start with the log likelihood. What is the log likelihood in the latent growth curve model that you guys have up? Point what?
386.
So it's minus 3016.386, not quite the same. What is your scaling correction factor?
1.0315.
Not the same, right? So it's close, but not exactly the same. What's your BIC?
6088.703.
Definitely not the same, right? Let's scroll down here. What do you guys have for a slope?
The same.
Okay, what do you guys have for an intercept? Don't have the same. Why don't you guys have the same intercept that I have? What's going on there?
Isn't it that thing?
Yeah, it's that thing. You're right. Right? So what we're actually talking about is this, right? This is where I'm sitting, and this is where you guys are sitting. What do you guys have for an intercept?
0.523.
0.523. Let's do this. So I've defined t, or happy as t. Let's go new time equals time. And how do I get my time to be equivalent to your guys's? Minus 1. Let's try that. So now let's go new time. Let's come down here. New time. Let's run that. Oh, it didn't like that because of the way that I did this, I just need to swap these around. Oh yeah, and I need to put this as my within subjects. Okay, let's try that again. Looks like it worked. All right, does this match? Nope, shouldn't yet. This? Nope. All right. Come down here. Do these match? Okay, so we've figured out that one of the differences between our two models is that one is looking at time starting at 0 and one was looking at time starting at 1. But our models are still not equivalent, right? And I told you earlier that the multi-level model is just a special case of the latent growth curve model. Now, when you guys are looking at your latent growth curve model, I'll flip over to it because I've got it in here. We have some residual variances here, 4, 5, 4, 7, 4, 8, blah, blah, blah. We also have variances of our intercept and our slope here, 2, 2, 4, 9, 8, 9. I'm going to jump back over to the long, run that again. Our variances here are close, but they're also not exactly the same, right? What did I say, 224 and 989? We have 227 and 984. This is the reason why. We have 0.488 here, right? But over here, we have a bunch of different residual variances. So let's make these models equivalent. Let's go back to our input file. Let's do this. Let's go T1 through T4 at 0.488. That is the average amount of within subject variance, right? That we got from our multi-level model. And we're going to save this. We hit run. If we scroll down, we'll see now that our residual variances here are all set to 0.488, right? They're set to be exactly the same. And now let's go back and look at our long. God dang it, where are you at? Okay, here is the multi-level model. Let's start at the very top. So you guys have run that, setting it to 0.488, correct? What do you have? No?
No, could you put it back in? Oh, he's gone.
All right. What do you guys have for a log likelihood now?
3718.233.
Wait, say that again?
Negative 3718.233.
Is that what everybody has?
That's just what I had. Okay. That's fine.
What do you have, Mark?
Negative 36.698.
Oh, so there's a little bit of rounding error there, huh?
Yeah.
Okay. And that probably has to do with the fact that this residual right here, 0.488, goes on and on and on and on within the context of this model, but we set it to be 0.488 and then stopped in the other model, right? Pretty close though. What do you have for a BIC, Mark?
I have 6064.468.
664.468?
No, 6064. Yeah.
Oh, that's interesting.
I think I did 4.8.
Oh, gotcha. And so the BIC actually may not match up perfectly, but the log likelihoods are what tell you if your models are completely equivalent or not. And so the fact that our models are pretty dang close to being completely equivalent, at least it highlights what I wanted to highlight here, which is that you can make the multi-level model is just a special case of the latent growth curve model. The BIC actually is oh, what's your scaling correction factor, Mark?
That's also different. That's 0.975.
Yeah. So the BIC and the scaling correction factor are going to be a little bit different based on number of model parameters that we've fixed, right? Because as soon as you start fixing things, then you change the BIC and you change model the correction factor. But the fact that our log likelihoods are close or very, very close makes me feel better about this. If we scroll down and we look at everything else within our model, every single number in here should also match. Fingers crossed. What do you have for the correlation between S and I in the other one?
0.133.
Yeah.
What?
Yeah.
Yes.
0.133?
Yeah.
0.132 is rounded.
That's pretty dang close. Yeah,
Yeah, I was
I'm
saying
guessing that a lot of this is rounding error because I'm doing point.
I was standing error is 0.031, and that's 0.032. So.
Oh yeah, yeah. Almost certainly that's a rounding error then. All right. Intercept and mean. What do you got there? Or I mean intercept and slope for happy and S. Same. And then your variance is down below. 984 and 227. All right. Well, unfortunately, not as perfect as I wanted, but pretty dang close to perfect, right? There's some rounding error here, but I think it does highlight the fact that this is really just a special case of the latent growth curve model. All right, let's do something else because I'm tired of looking at this. Let's open the other one, which should be, it should look like this. And by the other one, I mean modules. I think the data set for it is called Crazy. Is that right?
Yeah.
I named it after my wife. Oh, that's on YouTube. Okay. It should be new data down here. New data.inp. Those are the ones that we want. Okay, so I've already done all the centering here for you guys, so you don't have to do this. But I want to talk a little bit about contextual effects and what these contextual effects are. So we have, does everybody have this? Are we good to go? Can I start rolling? Who needs a little bit more time? We're all good? Okay. We have average amount of stress per day per person. This is across 100, I think 101 different people. This is real data that we've collected. We have within subject anger, and that is the amount of anger that a person has on a given day. We have between subject anger, and that is that person's average amount of anger centered. We have within subject happiness, that is that person's average amount of happiness on a given day across roughly 15 days. So we have, for each thing here, roughly 15 measurements of happiness per person, 15 measurements of anger or mad per person, 15 measurements of stress per person across 100 people, so roughly 1,500 observations. And then we have between subject levels of happiness, between subject levels of anger. How many observations do we have for between subject levels of happiness and between subject levels of anger then? If we have 100 people, we should have how many measurements of those?
300.
Nope, just 100. We have one measure for each person, right? Each person has their average level of happiness, their average level of anger at the between subject level. Why don't I do a between subject stress? I just have one measure of stress there. It is your main outcome variable. You don't have to have, you technically can have a mean level of anger and use that as your outcome variable also, and your model will be exactly the same. But with this, you don't, with M plus or with any other software, you don't have to parse that variance across because it does it for you. That's part of the beauty of multi-level modeling, is it's looking at, and even if it didn't, if mean stress was just a between subject variable, and we added it at the within subject and added it at the between subject, our within subject would actually, we would have no variation, right? And our between subject would collapse to a regression analysis, right? A straight regression analysis. Yeah. Okay, so let's walk through setting this up. We're going to do assessment equals 1. Do I have assessment up there? Yeah, I do have assessment up there. Okay. And this is just something that I used to tag each person's day here. Okay. Cluster equals ID. What are we going to put in the within subject model? If you specify something here as within subject, that means that when we actually start building the model, you cannot put it at the between subject level. So for within subject, what do we have for within subject variables? Because we want to be able to put stress at both levels, right? Yes, so let's do WS mad and WS happy. At the between subject, what do we have? BS mad and BS happy. And that's it. We've specified which variables are within subject and which variables are between subject. Again, for each person, we have roughly how many of these? 15 for each person, which means each person has how many slopes? Roughly 15 slopes. And across all of those slopes, we're going to get an average per person, right? And then down here, we're going to get an average across all people. Let's specify our model here. Okay. Let's do something like this. Let's say that we are going to remove any possibility of a random slope. So this means that we want to actually get the true measurements of slope at level 1 and the true measurements of slope at level 2. Okay, we're going to go MD stress on these two variables, right? And down here, MD stress on these two variables. Now, if we do this, we can't actually predict our slope at level 2 from anything, but this will give us true contextual effects, right? You'll see what I mean here in just a moment. Are we all ready? Let's hit save, and let's hit run and see if that works. Kind of didn't look like it worked. Oh, it did work. Okay. It's a completely constrained model, right? Or a completely saturated model, so you're not going to get any types of model fit. And so here we actually get these values at level 1, values at level 2, our true intercept of stress, our residual variance. So we do have a significant random intercept. But notice that because of the way that we specified this model, we don't have random slopes, right? We're saying like we are fixing the slopes at level 1 to be this, and we're estimating the slopes at level 2 to be this, and we're not allowing for random variation in slopes. However, it's quite possible that we do it. Let's walk through what these things mean. This means that on any given day, for the average person, right, as anger increases by 1 unit above their mean, we see an increase of 0.6018 in stress. And as happiness increases by 1 unit, or as happiness decreases by 1 unit from their mean, we see a decrease in stress of minus 0.329, right? All of these are in relation to this, and this is just across all people. As anger increases 1.183, or as anger increases 1 unit, we see an increase in average stress of 1.183. And that's between subjects, right? That means that technically what we're saying here is that an angrier person has more stress, right? And a happier person has slightly less stress, though it's not statistically significant, because these are all between subject values, right? So this is really denoting how angry a person is in general. These up here are relative to yourself. So when your anger is 1 unit above your average level, your stress is 6.608 units above your average level. And when your happiness is 1 unit above your level, your stress is 0.329 units below your average level of stress, right? Does that make sense? All right. Let's do something a little bit different. Let's go S1. Actually, let's call it M1. Now, one of the cool things about M+ is it allows you to specify what slopes are random and what slopes aren't random in a multi-level framework. And so we're going to call M1 mad slope 1, and we are going to call H1 our random slope of happiness at level 1. Down here, we're just controlling for mean levels of anger and happiness, right? And we hit run. Because we specified those 2 random slopes, M+ will not give us any type of fit indices. It doesn't matter because our model was fully saturated. We weren't going to get fit indices anyway. Come down here. Now, what were listed up at level 1 are no longer listed up at level 1. Remember, we had slopes up here before? They're gone, but that's because they've just been plucked and moved down to here. The values have also changed slightly, and that is because we've now allowed these slopes to vary randomly. And here are our random variance components for those slopes. Let's say that yeah, go ahead.
What was the significance of adding that M1 and the H1 for each of these?
If you don't do that, you can't specify a slope as random versus not random.
So now it's not random.
No, now it is.
Now it is.
Before, all we had was a random intercept. Now we're allowing those slopes to vary randomly as well. And this is saying that there is significant variation and slopes within people, right? That means that each person has an average slope, and that average slope varies significantly within people, within person, right? And the average within person slope, if you take all of the slopes and you divide by 100, or not by 100, in this case by, let me scroll up, by 1,179, then this is the average slope for anger, right? And this is the average slope for anger, taking the 101 average slopes, adding those together, and then dividing by 101. Does that make sense? We have a total of 1,179 slopes.
So like if you didn't do the M1H1 thing, you would still have a relationship between stress and within person, mad and happy.
Yes.
But those aren't random.
Correct.
So you wouldn't get the same.
You're gonna get
The slope would still be.
the slope is still going to be close. Like let's have a look at this. And actually,
I just don't get like
why we're
random
doing
does.
this. So it allows for the fact that people can vary across days in this particular case, right? As I said before, if people don't vary across days, then it collapses to a straight regression model, right? If our slopes within days don't ever change, then it collapses. Then you don't need to really worry about level 1 or trying to understand the variability in level 1. The nice thing about the model, about this model, is being able to say that people do vary people do vary within themselves, right? That's really what you're able to kind of make a case for here. So,
Is the intercepts like as random or?
the intercept gets set as random regardless. Now you can change that. In fact, we can change this here as well. So we can come down here and we can say M1 at 0, H1 at 0, and even MD stress at 0. And if you find that you don't have significant, and so this actually, let's do this. This will set our model to be exactly the same as we did it before without these statements, right? It constrains our variance to be 0, and our slopes go back to being exactly what they were before, which is not all that different from before anyway. Right here. And now we have no random variance. So 608 and minus 0.329, if we do this and this, .608 and minus 0.329, right? And if we go back and put M1 and what did I call that? H1. We get slopes that vary, that are not 608 and 0.329 anymore, minus 0.329. They're close, right? And that's because our variation in those slopes is not a lot, but it allows for a more accurate estimate of what's going on at the within person level, right? You wind up now taking a mean that accounts for random variation within person. A mean slope that accounts for random variation within person. And sometimes it doesn't matter, right? And if these were, like I said, if these were non-significant, then the random variation the slopes would not be different at all. But the more variance that we have here, the more likely that these things are going to be vastly different. here our p-values are small, right? Like we barely have significant random variance. We do have significant random variance, but that's why these are actually pretty close to what it is if you fix it to 0.
So in calculating those numbers, how does the process differ?
How did say that again?
Like in the mathematical calculation, how do those processes differ? Like between doing it like that, where it takes into account how people can change over time, and when you just
So what it's doing, let me see if I can explain this well. In the one instance, it's just saying like each person just has this, right?
Yeah.
And then it's taking the average of each of those for each person, right? And giving you like a single average across people,
Yes.
with the idea that everybody is basically this, right? In the other one, it's saying like, hey, we have a whole bunch of different things, and we have this one average that is comprised not of 101, but of 1,179. And so with that additional variance, we're able to show that this winds up being, at least in this case, slightly different from what we would get here.
Oh,
Does that make sense?
yeah.
Okay. I was going to say something else. I don't remember. Okay. All right. I have lost my train of thought. Are there any questions over this right now? Does it make sense to people? Who does it not make sense for? Right now, we're not looking at interactions. We're not thinking about cross-level anything. I just want you guys to understand that we're talking about parsing variance across these levels as a function of all of the potential slopes, or as a function of each person having a single individual, a single slope, right? So a person could have one slope that gets used to model the average slope, or a person could have, in this case, 15 slopes that gets used to model the average slope. And by fixing the variance to 0, you're saying we're going to constrain everyone's slope to be a single slope. That means that we're going to use 101 slopes to model, to look at this model. By allowing it to vary freely, you're saying we're going to use 1,179 slopes to model this. And assuming that there is enough variation in those 1,179 slopes, then we would allow that variance to be freed. And if there's not, the model will tell you, and sometimes the model won't converge if you are trying to specify significant random variance in slopes or intercepts, in which case you can go back and just fix it to be 0, right? And the way that you fix it to be 0 is just like I did earlier. You just constrain that. Now, if we do this, let's see if we can get it to not like this, because stress definitely does have a significant random variance component. On the intercept, oh, it still worked. That sucks. I was hoping it wouldn't. But none of these model parameters are actually all that different, right? Was there a ton of variation in stress? Do we recall? There is a fair amount, but I guess not too much, I guess. Okay. That is everything that I have for today, I guess. Are there any further questions before we wrap up? No? Yeah.
Is this the craving data?
This is from the same data set as the craving data. Yeah. Yeah. That's a paper that Daniel's working on. It's kind of unrelated, but all right. If there aren't any other questions, then we will call it quits for today. Your guys' homework is going to be very similar to this. It's going to be contextual effects, looking at variation kind of within. Oh, wait. me see. Let's do one other thing before we wrap up today. Let's do this. I'm sorry. Everybody was getting excited that they were going to get out of here. One cool thing that we can do is we can actually look at exactly how our variance kind of breaks out by level. So to do that, we just put our variable, like this variable is not a within subject or a between subject variable, right? This is stress. And we're just going to list stress at each level here, okay? We're going to list it as a use variable. It's the only thing we're going to list as a use variable is MD stress. And let's hit run. And so we get variance at level 1, variance at level 2. And you can add these two together to get your total variance. So I'm going to grab my little handy dandy calculator here. 0.37 plus 0.379 equals 0.749. So our total variance here is 0.749. And then we can calculate our ICC, which is the amount of variance at any one of those levels. 0.379 divided by what did I say, 749? You get an ICC of 0.506 or 0.51. That means that 51% of our variance is at the between subjects level, and 49% of our variance is at the within subjects level, right? Now this becomes important if you want to use those parameters that we just had to explain variance, because if you have huge amounts of variance at the within subject level and none of your let's take a hypothetical here, and just FYI, that's not a perfect measure of your ICC, but it's pretty close. M plus will also give you an ICC. Well, I guess it is a perfect measure of ICC, 0.506. I didn't think that, I thought that using MLR gave you kind of a more precise measure than just adding and dividing, but there it is. That's your ICC. That's the amount of variance that's at the between subject level. So let's say that you run, this is a hypothetical question. Let's say that you run a model and your ICC is 0.9. What does that mean?
90% variance within subject level, so very less variance between subjects.
Yeah, no, other way around. Other way around. If your ICC is 0.9, that means that almost all of your variability is between subjects, and there's very little at the within subject level, right? Now let's say that you have two predictors at the within subject level, and they are predicting 80% of the variance, really, really strong predictors of the within subject variability. And at the between subject level, they predict 0.01% of the variance. What do you make of a model like that?
I think at level 2, it is majorly within subject.
Can you say that one more time?
Sure. So you have a model that has an ICC of 0.9. At level 1, your predictors are accounting for 80% of the variance. At level 2, your predictors are accounting for 0.01% of the variance. What do you make of this model? How do you explain that? What do you say? I don't mean explain it like what's going on. What I want you to tell me is like, is this model, what is this model telling us?
So there's very little variability, like whatever the level 2 is.
Other way around.
Huh?
Other way around.
There's a lot of variability at level 2?
Yeah.
I thought you said,
Yeah.
I thought you said
The
That's
ICC
another
is-
random variability that's not being counted.
The ICC is 0.9, so that means that the vast majority of the variability is at level 2, right? It's between subjects. Like 90% of the variability is, the 90% of the variance is between subjects, which means only 10% of the variance is within subjects, right? We're able to account for 80% of the within subjects variance and 0.01% of the between subjects variance. So what does that tell us?
So the predictors are.
Go ahead, God.
I was gonna say, maybe there are other variables not accounted for that are causing the variance, that the ICC is detecting.
Yeah, for sure. There's something we're missing everything at level 2, right? At level 1, we have 10% of the variance, and we can account for 80% of that, which sounds awesome. Like, hey, we're accounting for 80%. You never account for 80% of the variance. But in the grand scheme of things, how much of the variance are we actually accounting for in total?
0.8 into 0.1, which is equal to 0.08. 8% of the value is actually good.
Say that again.
8% of the value, because it's 80% of the 10%, so it's 0.2 to 0.1, that's 0.08.
80% of 10% of the variance. Yeah.
It's
Which-
0.8% of total value.
Which is just under 8% of the total variance, right? It's not quite 8% of the total variance. And
So
we're
then for level 2, we're accounting for like 0.
basically 0, yeah. So while that level 1 model, and so you see this all the time in papers, like, oh, we're able to account for this huge amount of variability at level 1 or at level 2, but the problem is it becomes increasingly easier to account for a lot of variance if there's just like very little variance to account for in the first place, right? And so you have to be kind of skeptical about some of these things. Yeah, go ahead.
And the ICC number that's produced and the syntax,
Yeah.
does that always refer to the variance in level 2?
It always refers to the variance in level 2, and I mean if you're unsure, you can quickly do the math.
To the math.
Yeah. So, all right.
So what do we do with that model? Is it like acceptable, not acceptable? What do we call it?
The one that we were just talking about, for example, I mean, it's acceptable. It's just it's not. It doesn't provide great evidence for anything, right? I mean, it provides some evidence, and I'll be honest. Like I do substance use research, and a lot of times when I do cannabis stuff. Man, if I can get a model to account for 8% of the variance in cannabis use, I'm pretty excited about that, to be honest. I listened to a talk one time by, I think it was Radenbush who had said this, who wrote like the first book on or one of the earlier books on multi-level modeling. He said, one person's residual variance is another person's career, and so I think being able to say like, well, yeah, I could account for 8% of the variance, and maybe somebody else can account for 20% of the variance in something, right? Like eventually these things add up. So I'm not saying it's not important, right? But I'm saying that it needs to be taken in context. So, yeah. All right, that is it for today. I will get your guys' homework up. I won't see you guys for 2 weeks. Have a great Thanksgiving. We won't have homework due until after Thanksgiving, so take your Thanksgiving break, and
This homework is due, the one that you're gonna post.
it'll be due the right before the last class, and then we will have that last class, and you will not have homework on that last class because I'm going to give you the exam that day. So, yeah, make sense? All right, cool. We'll see you guys.